Section 1.6, a library of parent functions. Believing that you can is half the battle, unknown. Below are graphs of 7 functions, and we know them as the parent functions. Just like our parents, we have, as their kids, we have similarities to them. So for example, my eyes might be like my mom's, my hair might be like my dad's. So in math, these parent functions, any functions that look like them will have similar characteristics. The first one is the constant function. And the constant function is basically a horizontal line crossing through the y-axis. In this example, it crosses at c. So this is the value c here. So the domain for this, as you can see, we're using all the x values. So this would be from negative infinity to positive infinity. And the range, the only y value being used is c. So c would be my range. And then this function, we need to determine if it's even or odd. If you notice, the graph has symmetry on the y-axis. Basically, if I fold this on the y-axis this way, this will fall on top of it. Since it has symmetry on the y-axis, then we say that it's even. And then this function is constant, and the interval that it's constant on is from negative infinity to positive infinity. So from here to here, this graph is constant. The next function is the identity function, also known as the linear function. And the equation for that is f of x equals x. And so you can see this is a line, and we looked at lines in section 1.3. And so the domain for a line is always going to be negative infinity to positive infinity, as we can see from the x values being used, or all the negative and positive values. And then the range is the y values, so we're going from negative infinity to positive infinity. This function has symmetry on the origin. As you can see here, if I fold on the y-axis and then on the x-axis, this will land on top of this. So we say that this is an odd function. And also we can see the exponent for x is 1, making it an odd function. This graph is increasing, and it's increasing from negative infinity to positive infinity. The next one's called the absolute value function. And when you graph it, it's going to be a V-shaped graph. So V-shape. The domain goes from negative infinity to positive infinity. We're using all these x values. The range goes from 0 to infinity, from here to infinity. This graph is going to be even since it has y-axis symmetry. If I fold on the y-axis, this line will fall on top of this line. So if I fold it this way. This has both increasing and decreasing. So it's decreasing from here, negative infinity to 0. So on this interval, negative infinity to 0, the graph is decreasing. And then from 0 right here to infinity, the graph is increasing. The next one is the quadratic functions. And these are going to be quadratic if the highest exponent of x is a 2. And this is a U-shaped graph. And so the domain goes from negative infinity to positive infinity. The range goes from 0 to infinity, 0 to infinity. And then this also has symmetry on the x-axis. So we say that the graph is even, since it has symmetry on the y-axis. If I fold it, this will land on top of this. And it has both increasing and decreasing. It's decreasing from negative infinity to 0. And then it's increasing from 0 to infinity. The next one's called the cubic function. And it's going to be cubic if the highest exponent is a 3. The domain goes from negative infinity to positive infinity, since I'm using all the x values here. And the range goes from negative infinity to positive infinity. This has symmetry on the origin, so we say that the function is odd. If you fold on the y-axis, this will land on here, and then on the x-axis, it will land on here. This is increasing from negative infinity, so from negative infinity here, all the way to positive infinity. This part here looks like it might be constant, but if we zoom in, the graph is actually keeps increasing. The square root function is a function with the square root here, and it starts at 0 and shoots up to infinity. So the domain was going to go from 0 to infinity, and the range is going to go from 0 to infinity. This is going to be neither. There's no symmetry. If I fold on x, there's nothing here. On the y-axis, there's nothing here. If I look at the origin, there's nothing for it to land on. This is increasing from 0 to infinity. The next one is the cubic root function. So notice it's has a cube root. And so the domain is still negative infinity to positive infinity. The range is still negative infinity to positive infinity. This is going to have symmetry on the origin. So we say it's odd. And this graph is increasing at every part of the x-axis from negative infinity to positive infinity. Go ahead and try the next one. I'll give you a second to look at that. So the next one's called the reciprocal function. So the domain here goes from negative infinity all the way to 0, union 0 to infinity. Then the range is going to go from negative infinity to 0 again. So we go all the way up to 0, but it's never going to touch. And then it starts at 0 to infinity. This function is odd since you have symmetry on the origin. If I fold it this way, it lands here, and then I fold it down and it lands here. Then we have that the graph here is decreasing from negative infinity to 0. And then the graph is also decreasing from from 0 to infinity. Then we have the next function, which is a square root function. So the domain is from negative infinity to 0, union 0 to infinity. So all these x values here. The range goes from 0 to infinity. This is going to be even since there's symmetry on the y-axis. And the graph is increasing from negative infinity. So from negative infinity, and then the graph is increasing to 0. And then the graph starts to decrease from 0 to infinity. This is negative infinity. Okay, so those are your basic functions. The ones that we're going to use the most are the following. Let me put a star next to them. So the ones that are used the most is the linear function, the absolute value, the quadratic function, the cubic function, and the square root function. And so those are the ones that we'll use the most, the reciprocal one. Okay, the next part is using step functions. And a step function looks like a little ladder. So you can see it looks like a little ladder. And so the definition for a step function is that step functions resemble stair steps. One common type of step function is the greatest integer function. And the symbol that is used is this one here. It looks like two little brackets. And we define it as the greatest integer less than or equal to x. So here, we want to evaluate the greatest integer. So the best thing to do here is remember what the definition is. Less than or equal to x. So I'm going to underline this part because this is going to be the most important part. And I'm also going to draw a number line to help us understand what this statement means. Okay, so if we're looking at f of x is -1, and if I plug it in here for x, then when we bring this out, the definition says that it's going to be the greatest integer less than or equal to x. Since -1 is an integer, then this is just going to come out as -1. My y would be -1. So this is just going to be -1. If we plug in -1/2, then -1/2 is not an integer. So -1/2 is located right here. Okay, and this is not an integer. And so by definition, we need to get the integer that is less than x. So the integer less than x would be this one here. So this is the integer less than 1/2, the greatest integer less than 1/2. So for -1/2, this is going to come out to -1. So another example, 1/10 would be somewhere in here. This is 1/10. Okay, so 1/10 is not an integer. So the greatest integer and keywords less than 1/10 would be 0. So we go to the left. So the first greatest integer less than 1/10 is 0, since that's the first one to the left. So that would be a 0. 1.5 is right here. Since 1.5 is a decimal, that means that that's not an integer. And so the greatest integer less than 1.5 would be the first one we see to the left, which is 1. And then 1.9 is right here. And again, 1.9 is not an integer since it's a decimal. So 1.9, the greatest integer less than that is to the left, which again would be 1. So when you graph these, we go from -1, gives us a -1, which is here. -1/2 gives us -1. And if we keep going, we would get to 0. And at 0, let me plug in 0 here. So 0 is right here. The greatest integer less than or equal to that is going to be 0. So at 0, we get 0. So we put a closed dot, but notice here it has an open dot because there's so many numbers in here that are going to be close to 0, but not quite at 0. So for example, -0.1. Well, -0.1, the greatest integer less than that would be -1. That's why it would be here. And then we have At 1/10, we have 0. At 1.5, we have 1. But at 2, notice what happens at 2. For 2, this comes out as a 2. So at 2, we have to go up to 2. So we use an open circle here because at 2, it's not 1. Instead, it's a 2. So we need to finish it by putting an open circle to include all these numbers close to that value. So let's try another one. Evaluate the function when x is equal to -1, 2, and 3/2. So again, if it helps, draw yourself a number line. So my function is f of x is equal to the absolute step function here, x, the greatest integer, plus 1. And we want to know when f is -1, what we're going to get. So we have -1 plus 1. Where -1 is right here, and you can see that it is already equal to the greatest integer. So that comes out as -1 plus 1, which is 0. So I'm going to make a little table here and just plug in when x is -1, we get y equals 0. For f of 2, I'm going to get, plug that in here. So f of 2 is over here, and that's already the greatest integer. So that's going to come out as 2 plus 1 will give me 3. And then the last one, f of 3/2. So that 3/2 is 1.5, which is right here. And so that is not an integer. So the greatest integer less than that would be the 1. So this 3/2 comes out as a 1. So we get 2. Okay, so that's how we would evaluate this function. So now we want to sketch it. So to sketch, we need some numbers. So I'm going to just choose a few here, -2, -1, 0, 1, and 2. So if I plug in -2, we get 1/2 times -2. And I'm going to go ahead and use a number line again, just so that we can see the numbers. So -2 is going to give me 1/2 times -2 is -1. So that comes out to -1. Since -1 is already an integer. F of -1 would give us 1/2 times -1. One-half times -1 is -1/2. So -1/2 is right here. And that's not an integer, so the greatest integer less than -1/2 would be -1. So we get -1. F of 0, 1/2 times 0. So 0 is an integer, so that just comes out as 0. And then f of 1, 1/2 times 1 gives me 1/2. So half is right here. So the greatest integer less than 1/2 is going to be 1. And then last, f of 2, I'll put it on this side. F of 1 is already an integer, so that comes out as 1. For this problem, for f of 1, we get 1/2 times 1, which is 1/2. And 1/2 is right here. So the greatest smallest integer would be 0. So for the 1, we get 0. If we plug in 2, right here, 1/2 times 2 gives us 1. That's already an integer, so my answer is going to be 1. And then for 3, if I plug in 1/2 times 3, I get 3/2. That's 1.5, so that's going to come out as 1. And then for f of 4, we would get 1/2 times 4 is 2. 2 is already an integer. And then 5 times 1/2 is 5/2, which is 2.5. So the greatest smallest integer would also be 2. So if we want to plot this, we have -2 and -1. This right here, -1 and 1. 0, 0 is right here. And then we have 1 and 0, which is right here. Then we have 2 and 1, which is right here. And then we have 3 and 1. So you can see your little staircase building up. And then we have 4 and 2. And 5 and 2. Yeah, so we graphed our points. Now we need to fill in these gaps. So if I was to choose anything between this point and this point, since they're not integers, it's always going to end up being -1. So I'm going to draw my line here. But at 0, we got 0, so this has to be an open circle. And so here I have that at 2, I get 1. So in here, for 2, I'm going to have an open circle. This should be open circle. And then for 3 here, I'm going to have a closed circle. I mean an open circle for my next one. And then this is going to keep going. Then we would have an open circle and so on. Okay, so this here is an open circle. And so that would be how we graph a step function.